Greetings, aspiring scientists. Welcome to my video today. We're going to be starting reactivity, the second half of the IB chemistry syllabus. So big day, but let's get into it. It's going to be mostly theory, not so many math calculations or drawings, I think. But some of the theory is pretty difficult. I'm going to go just maybe a step beyond what's required for IB chemistry, just because I think it's important to understand as usual. But everything will certainly help you explain these concepts. So let's go to my slides. So reactivity 1, what drives chemical reactions? 1.1, measuring enthalpy changes. So I think I've used this word a bit in some of my other videos earlier in structure, talking about like lattice enthalpy in solids and things like that. And at the time I said it's just energy, think of it as energy in joules. And that is true, but we're going to more clearly define it today. So guiding question, what can be deduced from the temperature change that accompanies a chemical or physical change? So this is pretty important. We want to be able to measure the temperature, either increase or decrease caused by chemical reactions, and then be able to say something about what actually changed in the chemical bonds or the compounds and elements and mixture that we have. So we'll try to work towards answering this question. 1.1.1 then, energy transfer in chemical reactions. So this brings us to thermodynamics. This is a huge field of study in chemistry and physics and engineering and probably biology as well. We're going to try to do the simple version. So thermodynamics is the study of energy states and energy transfer in a very broad sense. You know, that statement probably encompasses a lot more than you're thinking. But it consists of a set of laws that scientists have come up with that we believe to be true about energy. And they are laws because we don't really have any evidence of them ever being broken. You know, we don't understand what happens beyond the observable universe, or like in the center of a black hole, maybe they might be broken there. But from what we have observed, these laws are not broken. And the first law is, in simple terms, okay, this is maybe not the definition you'd find in a dictionary or a textbook, but energy can neither be created nor destroyed. In a set system, like a place in the universe, energy can't be created or destroyed, only transferred between some versions. Okay, so with that said, what happens in a chemical reaction? Usually, energy is converted between chemical potential energy in chemical bonds. And really, if you think about it, this is electrostatics. It's positive and negative charges being attracted to each other and releasing energy when they are able to come close. That's kind of potential energy, chemical potential energy. And then heat, which is not temperature. We need to make that distinction very clear early on. Heat is an energy transfer, an energy change, whereas temperature is some type of measure proportional to average kinetic energy. But they're related through an equation, which we might get to later. But we know heat, energy, and temperature are related. There are important equations that link them together. So we can measure a material's current temperature or even changing temperature using a thermometer, a special instrument that can tell us degrees Celsius or degrees Kelvin. Usually they'll be like some kind of liquid encased in glass with a analog line system that tells us degrees, or there might be just like a metal stick, digital one that through conductivity or some method determines the temperature and digitally displays it on a screen or display. So thermodynamics in chemical reactions. You guys probably have seen chemical equations, I hope, by now. You often have reactants, such as A plus B. They go to new products, such as C plus D. This is just one example that has two reactants and two products, but you can have any combination of numbers. So now we're also going to consider what energy change there is in chemical equations like this. X joules of change. Joules are the unit of energy and enthalpy that we'll be using. So this energy can be released or absorbed. If it's released, this will be a negative value. If it's absorbed, it will be positive, meaning it's required to put into this system. So this is sort of a diagram that you often see on websites or textbooks. System, surroundings, and then the universe, which is like the total of everything. So the universe is composed of what we can categorize as a small system, plus everything outside that system is its surroundings. So you often see like your chemical reaction beaker is labeled as the system, contents of flask, and then outside of that is labeled the surroundings. But I see a lot of students make a mistake on what the system and surroundings actually are. So look at what I've written here. In thermodynamics, a system and its surroundings make up the universe. In many of the examples we will see in IB chemistry, the system is the chemical reactants and the environment is the solvent, atmosphere, and container, okay? So even though this diagram is pointing at the beaker saying system, the system is the chemical reactants that are involved in the chemical reaction, okay? It does not include the container, whether it's glass or plastic or metal or whatever. That is actually the surroundings. It does not include the solvent. So you might just have what's called a neat reaction that doesn't have a solvent. It's just the reactants forms the volume of what you're working with. But very often we do have a solvent like water or ethanol or whatever. If they're not chemically reacting, they are not the system, they are the surroundings. And also the atmosphere around this container is, of course, the surroundings, okay? So try to clearly understand that. The system is the things that will be chemically reacting and changing their chemical bonds. So there's a couple different systems that we can have. Some of them are more common in high school than others. So we can have an isolated system where there is no exchange of energy and no exchange of matter. They're blocked off or insulated or isolated. This would be a very nice system that we could do controlled chemical reactions in, but it's so difficult to build an isolated system, a true isolated system in high school, that we often are not able to work with isolated systems, but you could in university or in your career later. Excuse me. Then a closed system. This is where exchange of matter, so, extra air or extra solvent or extra reactants and products cannot enter. We have a set amount that we're working with. But we can have exchange of energy. So as the molecules and atoms inside your container bump into the walls gain kinetic energy, vibrational energy. They'll then bump into the atmosphere around it, and you have a net transfer of energy from your system to the outside, or possibly from the outside to the system. There is energy transfer allowed. And this is often what we work with in the laboratory. And then an open system is just everything is open, so gases can leave or enter. Same for anything else, basically. It's just open. Energy as well can leave, of course, or enter. So important points about heat transfer. Heat naturally flows from higher temperature object or area to a lower one. This is just true. It's kind of one of the laws of thermodynamics, I think. The word naturally, though, is important. Like, we can pump and force energy to go from cold to hot if we really try and really put in effort and energy. But naturally or spontaneously, it flows from high to low. And this difference in temperature is called a temperature gradient. Heat can be transferred in several ways. You'll definitely learn about this if you take physics classes, but there's conduction, contact. This is like where the atoms and molecules actually physically collide with each other and transfer their own kinetic energy. There's convection. This is sort of like mixing of fluids. It can't be done in solids, but liquids and gases definitely can have convection. This is where, like, as the material heats up, it expands and usually needs to rise as its density gets lower. And then as it cools, or as cool material approaches, that becomes more dense, gets heavier, contracts, and falls downwards. And so convection is just more of atoms or molecules, particles with different kinetic energy moving past each other into different areas and spreading out the average kinetic energy values. Then thermal radiation. This is important as well. It's electromagnetic waves. So you might not realize it, but when you have an oven or a fire, most of the heat coming off that is not conduction or convection, but rather infrared waves, I think caused by, the particles in the fire or heat source accelerating or decelerating, changing their speeds. As they do so, they release electromagnetic radiation always, and that's IR usually for low temperature things. Low in a broad sense, I just mean not superheated. But we're mostly going to be, I think, concerned with conduction and convection because we're mostly dealing with just aqueous solutions that have small temperature changes. Heat is thermal energy and therefore can do work. And in this unit, we'll consider the work to be increasing the kinetic energy of particles, increasing the kinetic energy of our sample on average. So work is kind of a useful type of energy. If you study physics, you'll know that. So work, I think, is often defined as a useful, concentrated type of energy that can do useful things for us, like move things, give large objects kinetic energy, that kind of thing. And so heat can do work, but it is never a 100% efficiency type of thing. Like if you have 10 joules of heat energy and you try to give something 10 joules of gravitational potential energy by lifting it upwards in a gravitational field, like on Earth here, you're not really ever able to get 100% transfer from heat that way. Anyway, that's a pretty complicated physics topic, but just keep that in mind. So enthalpy, real definition. We'll call enthalpy H, label it with an H. I don't really know why. Maybe because one of the scientists who worked on this is Hess. But the equation H equals U plus PV. Let's go through this. So this represents the internal energy of the system, labeled with U, plus the product of its pressure and volume. So U is just a type of energy, and pressure multiplied by volume is also a type of energy. You might know that pressure can be measured in units of joules per meter cubed. So how much energy do you have in some space? And then just multiply that by the volume, the space, you can get an amount of energy. So these units both become joules. That means H is also units of joules, just a certain definition or collection of energy. Internal energy is composed of kinetic energy and potential energy. And we have to be very careful with this statement, though. As I was thinking about this and making this video, I was like, if internal energy is kinetic energy and potential energy, why does enthalpy not increase when I drop an object and let it fall to the ground? It's increasing its kinetic energy from 0 to some number as it falls to the ground, but I know that its enthalpy doesn't increase. So why is that? This kinetic energy is a special type of kinetic energy. It's inside the material and it involves random motion of the particles. in the 3 dimensions of our world, it's not, set to any particular direction, such as when I drop this, everything is moving downwards. We're not talking about that type of kinetic energy and that type of energy in general when we talk about enthalpy. We're talking about random movement of the particles inside the material. One way to think about it is if I drop some material, if you just zoom in to the material itself, it doesn't know that it's falling or that it has some certain overall speed, because every particle has the same speed relative to each other towards the floor. But this type of kinetic energy that I'm talking about inside the material, everything knows or can observe around it that other particles are moving with different speeds, different vectors, different directions. That's the kind of kinetic energy that makes up enthalpy. Okay, what else? So it's very difficult to measure this directly. I don't even know how, but we often measure it as a difference, delta H, between initial and final states. So at time point A, time point B, or initial state, final state, what does it look like? It's going to have units of joules, or often joules per mole of reactant, or kilojoules per mole is fairly common. So for the enthalpy change, delta H equals delta U plus delta pressure times volume, okay? The delta difference operator is kind of just like if you apply it to the left side, it applies to everything on the right side. So delta H equals delta U plus delta PV. Now, we're going to simplify this even further. In liquids and solids, delta H is often approximated by just the internal energy change, delta U. And the reason is that they do not change their volume or pressure when heated or cooled very much. And it's even beyond this. It's like if we're doing this in an open kind of laboratory setting, we often have constant pressure on the surface of our material. And so this P, there would be no delta P. The P is some constant, just atmospheric pressure. So it's really just the volume change we would be considering. And if you think about it, if you have like a block of wood and you heat it up 50 degrees Celsius or 50 Kelvin, an increase. Does its volume really change? No, you can barely measure it. The same thing could be true for a container of water. If you heat it from 0C to 50C, you almost can't notice any volume change in that. So for our purposes in high school and IB, we consider delta PV to be essentially 0. And that makes things quite simple, just delta H equals delta U. Okay. One thing I will say though, one of my students did their EE on hot oil near its smoking or flash point. So he was heating oil up to like 250 degrees Celsius. He filled the beaker up 2/3 of the way, but when it got to 250 degrees Celsius, it actually started overflowing. So depending on your material and your amount of temperature change, you might actually have significant volume changes, which means you wouldn't be able to use this simplification. So just be aware of things like that. Okay, so this heat energy approximation is often written with Q. Big Q or little q, I've seen both. That gives us Q, the heat, is approximately equal to delta H, the enthalpy change, approximately equal to delta U, the internal energy change. So just to break down this equation a little more, going back to the regular enthalpy equation, H equals U plus PV, enthalpy, H equals U, internal energy. I should also write that. Okay, and I might have mentioned this in my previous video, but internal energy is essentially just another definition of energy, a certain collection that contains two things, kinetic energy and potential energy. The kinetic energy is, as I mentioned, the random motion of the particles in your sample. And the potential energy is more due to intermolecular forces. But there are some things about these. So the kinetic energy is always positive or zero, okay? If something's not moving, it's zero, but that would be like absolute zero, kind of theoretical idea that we haven't really ever observed. or it's positive, right? If it has a speed, it has a positive kinetic energy. This is very high for gases, this EK, but it's fairly low for solids. They can only be vibrating a little bit. On the other side, though, a bit more complicated, the potential energy, EP. This is always negative or zero. Okay, the highest value that it can be is 0. And then it's negative if there's more sort of interactions between the particles, more attractive forces. So as I've mentioned before, you can kind of think as a positive and negative charge that are infinitely separated. As 0. Okay? This is supposed to be like quotation marks because it's arbitrary. It's kind of just what somebody said. Someone decided this is a good idea, and I agree with them though. So this is the 0 situation. And you can kind of think of this as you standing on the ground of Earth, okay? That's the normal state. But when they approach each other, it's like falling down a hole. So if I'm here at 0, me on the ground equals 0. If I fall down a hole, if the top was 0, well, this has to be lower than that. This is, so I'll just say this is less than 0. It has to be negative. And this makes sense because for me to get back to 0, I need to like jump and put in energy or climb, put in positive amounts of energy, actual amounts of energy, just to get back to 0. So when a negative and positive charge get close together like this, okay, this is EP less than 0. Just like my diagram above. And it will be, very much less than 0 for solids, highly negative. So we can say the top is EP equals 0 when they're very separated, and they're approximately infinitely separated when we have a gas, right? They're very far away. We assume that they don't interact very much. So to get those positive and negative charges to separate again, we would have to put in work from outside or put in energy from somewhere else to separate them. Okay, this is really important for physics, especially HL, but it's also important to know for chemistry, I think. It's really nice if you can really understand the enthalpy equation. Okay. So let's move on. So enthalpy change, exothermic reaction, and endothermic reaction. In an exothermic reaction, our system has a bunch of chemical potential energy. It's not very stable. It's going to reorganize itself to become something more stable, but in the process of doing that, releases heat, releases energy. So our system before the reaction, if we have this little graph where the y-axis is like enthalpy, higher is higher enthalpy. Our system before and our system after has a difference. After is underneath, so our delta H here is negative, less than 0. Delta H of the reaction. RxN is sometimes an abbreviation you'll see for chemical reaction. So our system loses energy and heat goes into the surroundings, the environment. So that could be the glass walls of the container, could be the solvent if this is being done in aqueous solution, and can be the atmosphere or the table it's on or whatever else. Endothermic reaction. So this will not go unless it is able to absorb heat energy from the surroundings, from the glass, from the table, from the atmosphere, from the solvent. It needs to get that energy to proceed forward. So our system before the reaction is low energy, and our system after the reaction is higher. So this delta H arrow goes from before to after, goes upwards. That's a positive change. Delta H is greater than 0. Okay, now I do want to introduce entropy as well. Enthalpy and entropy, you'll often hear, are things that go together. This is not really required for SL chemistry. However, I think you should still know about it. At least know what it is, know that it exists. And I'll introduce it simply here. Simply put, it represents the amount of disorder and disorganization in a system. Very difficult to measure this directly as well, but again, it's often measured as a difference, delta S, between 2 points, initial and final state, in units of joules per Kelvin. So it's like energy units per temperature. The second law of thermodynamics says that total entropy in the universe is always increasing. Okay, so you might have a small system, and it is possible to increase or decrease the entropy of that system. But if you decrease the entropy of this system, it must be true that somewhere else entropy has increased by a greater amount. Okay, that's what this statement means. The total entropy in the universe must always be increasing. It's a really interesting idea. I'd go recommend watching Veritasium's YouTube channel video about entropy to really learn about it. But I'll explain a little bit more here. So there's 3 levels of maybe entropy definition that I could do. The first is the degree of disorganization. As I said, how messed up things are. The second, then, the degree to which energy is spread out. So if energy is, in a concentrated kind of packet or form, that's lower entropy. Whereas if it starts to spread out and become less useful, that's higher entropy. You can think of shooting a bullet. A bullet from a gun has like a concentrated amount of kinetic energy. It can hit something and do something, right? Break something or do some work. Whereas if it collides with, let's say, a block of concrete or something, and it splits the concrete into a bunch of small pieces, that energy is now more spread out. It's got many different directions and vectors, and many more pieces contain that energy. I'd say that's a more spread out amount, even though there was essentially a transfer of energy from the bullet to these pieces of concrete. In the second state, the concrete kind of exploding in all directions, it's less concentrated. All right, third, the number of possible microstates. This is the most kind of like theoretical or physics version of this. Configuration of particles. So it's asking kind of how many ways are there to arrange the particles in your system? How many locations can they be? How many, movement vectors and momentum vectors can they have? That kind of thing. How many ways are there to arrange them? If there's more, it's higher entropy. If there's less, it's lower entropy. And there are equations for that as well. I'm not getting into that, but in HL physics, in IB, you would. So the entropy change equation is often given as delta S equals delta Q over T. So it's a heat transfer and energy transfer at some temperature. And we put that temperature on the bottom of this equation. Oftentimes, for simple high school things, this will be done at one constant temperature, although I think the temperature could be changing in very complicated real situations. But that's where the units of joule per Kelvin come from. So this will be important for HL chemistry, definitely, to find out whether reactions are spontaneous or not. But for SL, that's all I'm going to say. But I do have some diagrams actually to show this. So imagine we have a bunch of like gas particles grouped up in the corner of a small container. If we just let it go, they will spread out over time. That's the natural thing, right? That's the spontaneous increase of entropy. And this also lets us know the arrow of time. This is how a lot of theoretical physicists and just very smart people in general, physicists, define time. It must be increase in entropy. If you look at two pictures, one where it's more disorganized and one where it was less, if there was no outside factors, somebody coming in to force these things into the corner again, then we know the left side picture came after the right side picture. That's the arrow of time, is increasing entropy. Same thing underneath. If you had a pile of bricks, maybe you had it organized on the back of a truck, but then they all fall off. Are they likely to stay in that organized structure? No, they're likely to be completely randomly spread out. Higher entropy situation. That's the spontaneous thing that happens, the more probable thing that happens. Entropy is also related to probabilities. So if you want to reorganize these things, if you want to put all these gas particles back in the corner, or if you want to rearrange all these bricks in a nice tower, you need to put in work. You need to actually do it yourself. And as you do that, you're going to be generating heat. You're going to burn fuel, burn calories, create friction, create sound vibrations. This creates more entropy in the surroundings and in the universe total than you can eliminate from the system being the gas particles or the bricks in these examples. So whatever you do, total entropy increases across the universe. Okay, what else? Important points. So a system at absolute zero, this is a concept I introduced in like the first lesson or two. Absolute zero is minus 273 Kelvin. This has zero entropy. It is completely organized, like you can imagine a completely solidified crystal with no vibration, and therefore there is no way to change the organization of these particles. They're locked in place. Zero volume, zero pressure, zero kinetic energy. And I am referring to the sort of internal random motion of the particles here as well. Whether or not enthalpy is zero, I'm not really sure. I think because we've set, those infinitely separated molecules as zero, I think enthalpy at absolute zero would be some like negative value that we don't really know, can't calculate. But this is a theoretical idea anyway, that all of these would be zero. It's hard to imagine what zero volume would even be like if something still exists. Enthalpy and entropy are state functions. Initial and final states are important, but pathway is not, at least for considering calculations. So I was often confused as a student what state function actually means, but I'll try to explain it again here. So the way that I like to think about it is a gravity field, right? Like just think about the room that you're in. In gravity fields in physics, things can have potential energy. If they're higher off the ground, right, they have more potential energy. And that potential energy has the potential to be converted into kinetic energy. If you drop it, gravity of Earth starts to accelerate it down to the floor, 9.8 meters per second per second. Now, it doesn't matter whether I take something on the table here and just push it off in one hit, or whether I lift it up, put it on a shelf, and then put it on the floor. The state of being on the table and on the floor were the same. They have the same amount of potential energy, whether or not the pathway was different, whether it was a direct path or whether it went up, down, across the room, and then down. The math for considering how much potential energy each has in the initial state of on the table and the final state of on the floor is independent on how it got on the floor, whether it was direct or not. Enthalpy is the same way, okay? So it doesn't matter whether you choose reaction pathway A or reaction pathway B. If the reactants and products are the same, then you know the enthalpy change will be the same as well. This forms the basis of something called Hess's law that we'll be studying later. Entropy is also a state function. So for mathematical calculation purposes, it doesn't matter how you go from point A to point B in this field of energy. If you know something was at point A and something then finishes at point B, you know the difference in energy between those. That's what we're saying with state functions. Very complicated idea, but I recommend you look it up a bit more if you need. Now, whether or not things happen spontaneously depends on enthalpy and entropy combined. Both of them affect whether things happen spontaneously. Things that would produce higher entropy are more likely to be spontaneous, and things that release enthalpy, exothermic things, are also more likely because you're going from an unstable chemical group to a more stable product. So quickly then, 1.1.2, exothermic and endothermic reactions. Just expanding on this a little bit. It's more of the same though, but we will see an exothermic process. Notice I say process and not reaction, because we can be talking about chemical or physical processes, even dissolving, boiling, whatever. This is a process which transfers heat energy from a system to its surroundings, exothermic. Endothermic process, chemical or physical, is a process which transfers heat energy from the surroundings into a system. So we can draw what's called a reaction profile. Very important to understand this. There's always questions about these on the exams. So we have energy on the y-axis, essentially potential energy. And then reaction progress on the x-axis. Okay, this is not time, but what you can think of it as is sort of percent completion, okay? So if we would have 25%, we'd be 25% along the x-axis. If we have 50% completion, we're at sort of the middle point. And if we have 100%, we're all the way at the far right side of this x-axis. So reactants for an exothermic reaction start kind of high. They do need to go higher though through what's called the activation energy. We need to put in a little kick to get things going. This is why even though wood burns, not all forests are on fire all of the time, right? They need a kick to actually start combustion going, and pretty much all chemical reactions are like this. Excuse me. So the actual delta H, the actual enthalpy change, is just the difference between where the reactants start and where the products finish. So that little, I guess, blue colored arrow on the right. And since it's negative, usually we would just draw that arrow with a downward direction. Like this. Endothermic then is kind of the opposite, but it also has an activation energy. It's the difference between the highest point that it ever reaches and where the reactants start. So again, usually these activation energies would be drawn just with upwards pointing arrows. Reactants all the way up to the highest point. Then they'll go down to products, but the products finish higher than the reactants started. Therefore, this is a positive enthalpy change. Delta H is positive. You'll also notice that the highest points on these curves are labeled with transition states. This is like a formation, a kind of mixture of the reactants colliding that needs to exist for a split second in time to actually move towards the products. But we'll get into that more later in the kinetics section of reactivity. So exothermic reactants are higher energy and less stable. Okay, anything higher on these graphs, higher energy, is less stable. Then endothermic reaction, the reactants are lower energy and more stable than the products. Very important. All right, so how about chemical bonding? We have A and B here, two chemicals that might come together to form a chemical bond. When bonds are formed, when chemical bonds are formed, energy is released from the system. Okay, so remember, just a few minutes ago, I had a positive and a negative charge coming together. We defined them separated as 0 and together as negative. Therefore, they have lost a positive amount of energy. Where does that energy go? It goes to the surroundings. Even though A and B might not be positive and negatively charged, it is the little interactions between the atoms and electrons and protons within them that forms this kind of process going on. So energy leaves as these finish with a more negative chemical potential energy. Okay, so energy leaves as these finish with a more negative kind of potential energy, chemical potential energy. So this is exothermic then. On the other side of that, bond dissociation. Okay, bond dissociation energy. This is always positive, okay? It requires energy from the surroundings. We're going from these positive and negative kind of charges stuck together. Again, even though A and B are atoms that might not have a positive and negative charge, the little interactions between the electrons and nuclei inside that do make it similar to this. So we're going to separate these. And to do that, we need to put energy in from somewhere. Therefore, this bond dissociation, breaking a bond, must be endothermic. Okay, positive amounts, real inputs of energy are required. So I have a little animation here I can probably show. So A and B are separated here. We'll allow them to come together. Boom, energy released. Now they're in a very kind of negative potential energy state. We need to put energy in to get them back to the zero initial state. Break that bond, endothermic, form that bond, exothermic. Okay, one more time. Atoms are separated, come together, energy released. To separate them again, we need to put in energy and break that bond. Think of it that way. All right. Moving on. So the way that we often do this is with calorimeters in the lab. Calorimeters are used to measure heat changes and enthalpy changes. So there's kind of like baby version, basic version that mostly everybody in high school uses, the coffee cup. So to accurately measure enthalpy change and whether a process is exothermic or endothermic, we need the system, the molecules, and the surroundings, the solvent, usually water, in the container. In a closed system, this calorimeter. What's the purpose of these labels? So we have the cup, usually polystyrene, styrofoam. We're going to double those up to double the amount of insulation we can hopefully get. It's a very good insulator. We're going to have the thermometer. We got to be measuring the temperature change of this liquid. We need a lid. We can't have too much gas exchange happening through the top of this cup. We want to contain the heat energy and the temperature change within the liquid. But oftentimes you do have to open up the cap a little bit to put in one of the reactants to get it started. We'll have stirring. We need to make sure that the reaction happens fast enough that heat isn't lost through the walls or through the holes in the top where the thermometer is. So it's better if the reaction happens faster. So more stirring going on. And we need that aqueous solution, of course. Oftentimes will be, or aqueous solution allows reactions to happen faster than if you just have like two solids together. Okay, but not that much going on. Then in industry or in chemical laboratories, university laboratories, you might have specialized instruments, the bomb calorimeters, much more sophisticated and controlled. So here, we're going to combust something, some fuel in the middle here. And I guess this could be done with any kind of reaction, but oftentimes it's done with these exothermic combustions. We have our liquid water surrounding this kind of explosion chamber. This is where we're going to try to capture all the heat. We do have stirring going on with the water to make sure it evens out, and whatever temperature we measure is a good average of the whole water contained in here. We have O2 inlet. If we're going to combust this, we need fuel plus O2 goes to CO2 and water. So we have to have extra amount of O2 coming in. And then we need that initial kick. We need that activation energy overcome. So we're going to do that with electrical energy. We have a potential current, electric current hooked up to our fuel, and we're going to turn that on and ignite it. And in this case, usually this whole thing is done in a very well insulated container, better than styrofoam, better than polystyrene. And, we'll hopefully capture all of the heat that is released from our system, the chemical bonds in the fuel, in the water there. We'll measure the temperature change and we'll get the accurate enthalpy change. But again, probably not doing this in high school. Okay, then to finish up, energy profiles. I've already shown this a little bit, just a bit more here with some maybe real examples. So zinc solid plus copper sulfate aqueous goes to copper solid plus zinc sulfate aqueous. This reaction is exothermic, so you can see the reactants start high, they go through the activation energy, and they finish low. Heat will be released. Delta H is negative in this case. Products are more stable than reactants, but activation energy is still required. Okay, not too much new there. So a real example of an endothermic one. This is also not even a chemical reaction. This is maybe just dissolving of ammonium nitrate, NH4NO3 solid, into water. NH4 plus and NO3 minus. So we're just breaking apart this kind of salt into dissolved ions. But it requires energy from the surroundings to do this. So if you do this in a coffee cup calorimeter, your water will get colder. Still needs to go through a transition state, up that big hump, and then finishing at products. Products are higher than reactants in this potential energy scale. So we should observe a decrease in temperature of surroundings, products less stable, but still activation energy required. So just one practice question quickly, it's not that difficult either. Consider this reaction: barium hydroxide plus ammonium chloride goes to barium chloride aqueous plus NH3 gas, ammonia plus water. Delta H plus 164 kilojoule per mole. Which of the following is correct? So we can go through temperature, enthalpy, and stability. Do we expect temperature to increase? We're going to be measuring temperature basically of whatever mixture this has going on. This delta H is positive. If delta H is positive, that means it's consuming this kind of heat from the surroundings. This energy is required to make this reaction go from left to right. So we're going to observe things getting colder, temperature decrease for sure. Enthalpy then, which has higher or lower enthalpy? Products have lower or products have higher. This is an endothermic reaction. So in this case, if you go back to my previous slide, you'll see products have higher enthalpy. So it has to be either C or D. But we've already said temperature decreases, so that's a hint. Stability then, products are less or more stable than the reactants. Our products are going to be higher up on the energy scale. Higher energy is less stable, always in chemistry and science. So we can say the answer to this will be C. Endothermic, decrease temperature that we measure, products have higher enthalpy, products are less stable. It's a nice little summary of most of what I talked about, excluding entropy. Yeah, but I think that's all I have for today. That was probably more detail than SL students need to know for sure, but I think it's good to know. The more you know, the better. You can always use things that are true in your explanations. All right, so next time we'll get more into how to actually measure and convert temperature into energy, and sources of error that might be in these kind of experiments, those kind of things. Thanks for listening. See you next time. Bye-bye.